Good morning, everybody. Thank you, Barbara, for inviting me to give this talk. So this is a recent published work in geoscience with the same title. So because this is a workshop, so I'm going to first report what we found in the paper, and then I'm going to give some arm-waving statements about nature of deep earthquakes. So the detailed work is done by my student Joshua Lee and the second author Leon Thompson, who contributed a lot in the anisotropy part, and Tom Lapin is a pathologist participating in the interpretation part, and Fang is a numerical modeler, so he did a lot of the finite difference 3D calculation to rule out cases. So there is a problem in seismology. Over the last 50 years, we observed for deep earthquakes, a significant number of them produce non-double couple components. If you look at radiated seismic waves, the problem is why so many deep earthquakes produce non-double couple radiations. And again, this is a very much developed field, and over decades. So Houston, the Treatise of Geophysics is a good starting point if you're interested in this topic. Nopov, Randall proposed the CLVD idea, and some of the experts are sitting right in this room, including Cook, Kawakatsu, and they wrote many papers, very systematic study about non-double couple components of deep earthquakes. Cliff Frolick yesterday gave a historical view of the deep earthquakes. However, he didn't tell you about the non-double couple, this problem. He also have a very good review paper. Recently, Fabry Cook, 2004 and 2006, proposed using this non-double couple component to invert anisotropy. Alkel found the implosion components in a CFA earthquake. That's our work. So the problem is, if you have a fault in an isotropic medium and you have a dislocation slip on the planar fault plane, you produce double couple radiation pattern. But the problem is we observe a lot of the non-double couple components. So for those of you who do not know how to read this beach ball, you just look at the crossing points. If it's a sharp corner, double couple. If it's a curved intersection, non-double couple. Okay, that's an easy way to distinguish. So those are just a graphic representation of the moment tensors. So we use the Harvard CMT catalog. And this is the number of earthquakes, a histogram of number of earthquakes versus departure from ideal double couple. So we call that CLVD parameter. If CLVD is 0, that means it's a pure double couple. If CLVD is non-zero, that means non-double couple. So what you see is you have a lot of double couple events, which is this type. In this diagram, it corresponds to zero departure from double couple. But we also have a lot of non-double couple events. So if you add them all together, they are a significant number. So the question, this is observation. So we want to understand what produces this non-double couple. Of course, there are many proposed explanations because this is a very developed field. For example, sources are different. Deep earthquakes, that's why we have this workshop. Deep earthquakes may be different in terms of faulting mechanism. Second one is multi-faulting, rupture on non-planar fault or rupture on multiple faults. So each one give you a double couple, but altogether, you add them up, you get non-double couple. So that's one idea. 3D path effects. So virtually anything can influence the wave field. Is a possible candidate to generate non-double couple components. Slab structure effect, because the slab, inside the slab you have high velocity core. Maybe you have a metastable olivine wedge. And also station coverage, because we have limited coverage of stations on the Earth, so maybe there's a bias. So we, in our inversion, or in the Harvard CMT inversion, and also anisotropy outside of the slab, we just listened to the talk. Maybe, that can affect the wave propagation, so that is also a candidate. Today I'm going to focus on anisotropy around the earthquakes within the slab, because I think that's the most important effect. So basically, using 3D finite difference simulation, we can rule out all these cases except the anisotropy around the earthquakes inside the slab. And for these two explanations, we do not really need them for most of the earthquakes. So basically, deep earthquakes are just like shallow earthquakes. They are dislocation events in anisotropy. Okay, the hypothesis, this is a hypothesis testing work. So the hypothesis is non-double couple radiation pattern of the deep earthquakes is caused by shear dislocation, just like normal earthquake, but in a tilted transverse isotropy anisotropy. Basically, that's layered, fine layering caused anisotropy. So before we go into the TTI anisotropy, let's first look at the VTI. That's more or less the industry type terminology. So VTI is a fine layering horizontal structure. So to characterize the VTI, we have to have the two velocities, VP, VS, along the symmetry axis, and also 3 parameters. We call them Thomson parameters because Thomson is a co-author, so we want to pay respect. So the first one is epsilon parameter, is called P wave anisotropy. Second one, gamma, is S wave anisotropy, and the third one is epsilon. It's a weird combination, which is very useful in industry, but not much in academia. It affects both the P wave and S wave anisotropy. So TTI is just a tilt. Okay, you have two angles, theta and the phi, and you tilt the VTI, you get a TTI. So that's our hypothesis. So the hypothesis is we don't invoke any unusual faulting mechanism. We don't invoke implosion or multi-faulting or rupture on a non-planar fault. This part is rupture on the planar fault by simple dislocation. And this one is the TTI anisotropy. So what you can see is here, this has 5 parameters plus 2 angles. You have 7 parameters to work for. So for moment tensor, it's a 3 by 3 matrix. It's a tensor, which means it's coordinate-free description of the equivalent forces for earthquakes. So you can compute the 3 eigenvalues because it's symmetric. You have 3 orthogonal eigenvectors and 3 eigenvalues. So lambda 1 is the biggest, lambda 2 is the intermediate, lambda 3 is the smallest. So you take the ratio lambda 2 over lambda 1, lambda 3, the maximum, put the minus sign, you got a CLVD. So we follow the Cook and Lay's notation. So the range of this CLVD is minus 0.5 to 0.5. So if it's 0, it's double couple. So the methods to invert for anisotropy is straightforward. So here we follow the work by Wawryka, 2004 and 2006. And of course, this equation, you can find this equation anywhere, in any textbook. So basically, here is our observed moment tensor. Okay, each earthquake, we have a moment tensor, 3 by 3 matrix. And these are the displacement of the slip and the fault area, S. CIGKL is the 4th rank elastic tensor. 81 components, 21 independent ones in most general case. NK and the nu L are the normal vector of the fault surface and the slip vector. So this is just equation which relates moment tensor observation and the elastic tensor which carries the anisotropy in it. So the goal is we're going to have a bunch of moment tensors. Hopefully they're clustered in a small region, a lot of earthquakes. And the moment tensors are all different, so which means they have different slip vectors, fault normal vectors. But we're going to invert a common elastic tensor, which has the anisotropy. So I have to point out, Varekuk first using this, he inverted the Tonga. He tested, this method works, but in a localized way, only in Tonga for 2 groups of earthquakes. And he further assumed the anisotropy is orthorhombic. So here we are going to invert tilted transverse isotropy, not orthorhombic. So I'm going to skip the inversion details. But I have backup slides. If you're interested in, we can talk more in the question and answer. So I'm going to show you some results. So we're going to use the Harvard CMT. Now it's global CMT. You can go there and download. So I have to say this CMT work is very important to our work. If these people, they don't do this CMT inversion, this cannot be done for obvious reasons. Okay, so date selection. So we looked at earthquakes global-wide, and we're going to apply some criteria. Eventually, we got 1,057 earthquakes global-wide in several subduction systems. Focal depth, we used greater than 100 kilometers. Magnitude range 5 to 6.6 from 1976 to 2013. And because the seismicity is scattered around, so we use, we give a very loosely defined slab earthquakes in the vicinity of the subducting slab. The slab geometry is defined by this paper, by fitting the best surface through the seismicity. And then we apply Froelic's criteria for better determined mechanisms, CMTs. Those are a set of criteria you follow for well-determined moment tensors. So after apply these criteria, we got 1,057 earthquakes in these subduction zones. First is Tonga, then Vanuatu, Java, Japan, and Aleutians. So first one is Tonga. So as I said, we're going to invert anisotropy. First one is the axis, symmetry axis, for each group earthquakes. Okay, we divide the earthquakes using k-means clustering method. So in Tonga, we divided into 8 groups. So black color is one group, pink is the second group, cyan is third group, and fourth. 8 groups. For each group, we invert symmetry axis and shear wave anisotropy gamma. So the reason we didn't get all other 5 parameters is because not all parameters are equally involved in defining the moment tensor. Just like in isotropic case, the moment tensor, you only have mu, there's no lambda, Lamé constant. So same principle works here, we only have gamma. So for group 1, we get a symmetry axis perpendicular to the slab interface. For group 2, we get a symmetry axis perpendicular to slab interface, and 3, 4, 5, 6, except for 8, Tonga 8. And if you look at the shear anisotropy, they're very large. The first group is 24%, second 26%, 27%, 30%. So they're large, but they are consistently large. Okay, they're large for all groups. And we also did the bootstraps to just resample the earthquakes and then redo the analysis. And this is the bootstrap for the inverted gamma. So in a lot of cases, they're symmetric. although the error bar is pretty big. So the second case is Vanuatu. What you can see is two groups of earthquakes. One is the pink, one is the black group. And again, the symmetry axis, which is the TTI symmetry axis, perpendicular to the slab interface. For these two groups, and the shear anisotropy is 25% and for 14%. So we look at this subduction zone. Again, we have two group of earthquakes. I have to say, when we do the inversion of the anisotropy, we do not have the slab geometry. So I plot the slab geometry only for viewing the inverted results. So for the inversion, we don't have location. We only have moment tensors for each earthquake. We don't use their location information, as long as they belong to the same group. So again, more or less perpendicular to the slab interface, gamma is pretty large, 29 to 30%. So this is different from a previous talk where you have shear wave splitting. You got a delay time. In order to convert delay time to absolute shear anisotropy, you have to know the layer thickness. So that's a big unknown. For this method, you directly get the shear anisotropy around the earthquake. So next subduction zone is Java. So again, of course, there are earthquakes all along this arc, but after applying the criteria, we got this group. Perpendicular to the slab interface, gamma shear anisotropy 31%. So again, it's consistent. Our most interesting case is this Mariana, Japan, Kurio slab, because there is a significant change in geometry. If you look at the Mariana southern part, you can see the symmetry axis is perpendicular to the slab. And they go to north, it changes direction. Again, always perpendicular to the slab, except for group 6 and 7. Those are two deep focus, deep earthquake groups. And again, the anisotropy is large, except this group 4. Seems not very perpendicular to the slab interface, but oblique, but more or less same direction. Again, it's around 25, 22, 30, 27% anisotropy. So let's look at this Alaska. Again, this side, we don't have a lot of earthquakes here, so we just have a very large group, this west group and the east group. Again, two groups with anisotropy axis perpendicular to the slab, consistent large anisotropy. So that's our model. We invert. So let's see how good the fit is. Okay, we have a model. We have to make a prediction about moment tensors, then compare the predicted moment tensors to the observed moment tensor. Okay, I gave this is a Tonga 4th group, Tonga 4. These four observed cases, observed one earthquake, second, third, fourth. So I'm going to use the inferred anisotropy I just got, use the symmetry axis, and find the best fit plan, and produce synthetic. So compare with the observed and the synthetic, observed and synthetic, observed and synthetic. So we're able to fit a wide range of moment tensors. So this one is almost double couple. Okay, this one is the very non-double couple. So the good thing is, this model, we were able to fit not only the double couple earthquakes, but also all the non-double couple earthquakes simultaneously. Actually, I have 1,057 of this comparison, but I'm going to give you one more. Okay, so this column, you can see the panels. Each one, this one is the observed, that one is the predicted using the anisotropy model. And that's one is, this Tonga 4, all of the Tonga 4 earthquakes. And I'm going to give you 10 seconds and tell me which pair is different. Find one pair is different. Okay, pretty much, I think somebody previously pointed out there's one pair is different. But, for 1,057 earthquakes, pretty much all of them are fitted very well. So that's for the radiation pattern, the beach balls. Actually, we have all 9 component 3x3 moment tensors available. So we just plot this first motion beach ball. So let's say the non-double couple parameter fitting, which is the FCLVD. If it's 0, it's double couple. So we compared observed and the synthetic. So as we know, if there is a one-to-one correspondence, we should get a 45-degree line. Okay. So for 1,057 earthquakes in all the subduction zones, we almost get a straight line. So this line, those are the dots. So for each earthquake, we have observed moment tensor. We could compute observed FCLVD. And we use our model. We predict the synthetic moment tensor. We compute the synthetic moment tensor, and we plot against each other. Okay, this line, what you can see is we have some large non-double couple earthquakes components. We have some smaller ones because that's 0. And we were able to fit both. Okay, both the large non-double couple and the small ones are fitted using the anisotropic model. And that's the anisotropy, but importantly is we only use the shear dislocation as a source mechanism. So there is no need to invoke a different source mechanism for deep earthquakes. That's for 1,057 earthquakes. Again, as I said, we fit both. So to summarize, the anisotropy versus depth, the previous talk also summarized similar syntheses. So we have gamma, that's the shear anisotropy, that's the depth. So each bar is one earthquake group. So because we have an earthquake group, so we have a depth range. So for example, this one is 350 to 550. And those are the Mariana, Japan, Kurio group 6, Tonga group 8, Tonga group 6, Tonga 7. So most of them are, if you look at anisotropies concentrated around this region, about 25%, 0.25. And what about the symmetry axis with respect to the slab normal as a function of depth? So we have intermediate earthquakes and we have deep focus ones. So most of the intermediate, all the intermediate earthquake groups, the symmetry axis perpendicular to the slab. So here it's really not 100% perpendicular. It's quasi-perpendicular. It's between 0 to 30 degrees. So which means the symmetry axis is only maximum 30 degrees away from the slab normal. And for two deep focus, we have 2 deep focus cases. One is similar, so 3 deep focus earthquakes, their symmetry axis perpendicular to the slab, but the 3 others, the symmetry axis is sort of parallel to the slab, which is very similar to previous talk, who have this layering. So I'm going to give you a schematic diagram here. So based on studying more than 1,000 deep earthquake radiation pattern, and we tested this hypothesis against a hypothesis, it doesn't mean all earthquakes are, rupturing along a single fault plane. Maybe there are a couple which can rupture multiple faults, but it has a significance in statistics. So for the intermediate groups, we have 16 of them. So all of the symmetry axis perpendicular to the slab. This is consistent with the dehydration and the metamorphic reactions. You have this fine layering, possibly water fluid pockets, generate very high anisotropy. And this layering is parallel to the slab interface. So we have 3 deep focus earthquakes. Those are below 300 or 350 kilometers, but actually different for different subduction zones. So 3 others, the layering is actually also perpendicular, parallel to the slab interface, but we also have another 3 groups. The TTI symmetry axis is parallel to the slab interface, but not only parallel, actually it's coincidence with the maximum compression stress axis. So which shows maybe that's a stress-induced fabric structure in those 3 deep focus earthquakes. And one candidate I'm going to do some arm-waving proposal is magnesite, which is a carbonate water, CO2 in seawater, react with ultramafic rock to form this magnesite, which is transported down to great depth, and they are stable. They are mechanically weak. They have brittle to ductile transition failure, which can cause earthquakes. So what is a deep focus earthquake mechanism? Is that really the metastable olivine phase change? So this diagram is from Green, Chen, Brzezinski, 2010 Nature paper. What you can see is the metastable olivine hypothesis only applies to earthquakes greater than 410 kilometer depth, which is below the discontinuity, olivine to wesleyite. They marked the area of anisotropic region. So here is the anisotropic region. This is a seismic anisotropy in mantle transition zone. But you also notice there's no faulting inside the cold slab. So no faulting. Actually, if you look at the flyer, you know, that faulting or any metastable olivine wedge, there's no faulting inside the slab. But even in Tonga, which is very cold and fast slab, we do see faulting. It's very clear. This is a work myself and several other people. We did high-resolution seismic imaging using the deep earthquakes, upgoing, reflect at the reflector, and produce downgoing wave back to station. So we do 3D migration, high-resolution imaging. You know, that's outside the slab in Tonga. That's faulting. Inside the slab, it's shallower, actually. It's a very strong reflector. It's very clear evidence that faulting is there. If faulting is there, where the metastable olivine is. So discussion is, I propose possible role of carbonates in generating deep focus earthquakes. The reason is the anisotropy induced by metastable olivine phase is going to be very weak. It's far weak than the value we inferred here. The other thing is the magnesite is mechanically weak. Its orders of magnitude weaker than surrounding rocks. So it can act as stress concentration points. The third is it has a ductile to brittle transition behavior, just like serpentine. So it's in this Holyoke paper. A single grain anisotropy is high, but I don't really need this high anisotropy single grain, because I think we don't need the inclusion to be highly anisotropic in order to generate effective anisotropy. So some ideas about origin of anisotropy. So we use inclusion model. So we have a very hard matrix, 8 kilometer per second for P wave, S wave 4, density. For the inclusion, we use a soft inclusion, which means we keep the VP and density the same, but we change the VS. And we use a finite element to calculate the stress strain field, and then do averaging to get effective anisotropy for this model. Okay. So it turns out if the inclusion is very weak, such as melt or fluid, there's a very simple formula to calculate the gamma, which is a shear anisotropy is 8/7 times a crack density parameter 8C. So the crack density, it depends on volume fraction, which is a porosity, and the aspect ratio of the inclusion. So the higher the crack density, the higher the gamma is. So if we have a 2% inclusion, if the aspect ratio is 0.01, we get a gamma 0.5. So maybe we only need 1% to get the anisotropy we need. This is a finite element modeling, again, show the same thing. If the VS in the inclusion is only 10% of the matrix VS, we got 0.3 easily. We just skip that. However, if the inclusion VS is 80% of the matrix VS, the gamma is very small. We cannot get very large gamma for metastable olivine. So prediction. For this earthquake, we have the mechanism in Tonga, and this has 11% non-double couple component. Same location, there's another one, earthquake in 1994. So if we put in our anisotropy model, and we can predict 11% non-double couple component for these earthquakes. So I'm going to give the conclusions here. I think most deep earthquakes, faulting mechanisms are shear dislocation. This does not exclude some of them, maybe not shear dislocation. Slab has very strong anisotropy around the earthquakes. For intermediate depth earthquakes, laminated fabric parallel to slab interface favors dehydration. Deep focus region, laminated fabric, 3 parallel, 3 perpendicular cases. Weak inclusions seem to be needed to create a large anisotropy. One candidate is magnesite. Olivine metastable stable phase cannot produce large anisotropy. Again, because this ductile to brittle transition, I think it's a good candidate to generate deep earthquakes. Thank you very much.